In this part of the lesson, we're going to look at linear equations. Now, we've just seen what an equation is and what a solution to an equation is, and we're going to focus on a particular type of equation for the next couple of lessons. So the first thing we have to determine is what makes an equation linear. Then we're going to talk about using the addition property of equality to solve linear equations. And then we'll talk about a multiplication property of equality that we'll also use to solve equations. And finally, we'll have to say a word about checking solutions. So now let's look at what makes an equation linear. So here's the formal definition. A linear equation can be written in the form Ax plus b equals c, where a, b, and c are real numbers and the constant a does not equal 0. So this is an example of a linear equation in one variable because we just have one variable, x. So let's look at some examples of linear equations in one variable. Here's our kind of abstract equation. Let's throw some numbers in. We have 5x plus 2 equals 12. In this case, a equals 5, b equals 2, and c equals 12. Now let's look at 3z minus 5 equals 10. Now in this linear equation, the variable is z rather than x, and in fact the variable could be represented by almost any letter. Now here I'm going to rewrite this as 3z plus negative 5 equals 10. So now we see that the value of b is negative 5. A equals 3 and c equals 10. 7.5x equals negative 100. There's no b here, but that doesn't mean b is nothing. In this example, b equals 0 because we're just adding 0 to the term with the x. A is 7.5 and c is negative 100. In the final example, we have a value of c, which is 0, and that's also possible. Here we have a equals 2 and b equals 7. In this case, the variable is t. Now, the reason why we don't allow a to equal 0 is if we multiply x by 0, the first term would just be 0, and then we would just have a statement b equals c, which might be true, it might be false, but it wouldn't be a linear equation in one variable. So now let's talk about the addition property of equality, because this is one of the properties we'll use to solve linear equations. So here's a very simple linear equation. N minus 5 equals 10. So what's a solution? Well, clearly 15 would be a solution to this equation because 15 minus 5 equals 10. We really don't have to work too hard to figure that out. The equation n equals 15 has the same solution as the equation we started with. N equals 15 has an obvious solution, 15. And I want to talk a little bit about vocabulary that we'll use while we're solving linear equations. So these two equations, n minus 5 equals 10 and n equals 15, have the same solution. The solution to both equations is 15. And when we have equations that have the same solution, we call them equivalent. Two or more linear equations are called equivalent if the equations have the same solution. So let's go back to our simple linear equation and now try to come up with that equivalent equation n equals 15 by doing some algebra. And what we're being told to do here is to add 5 to both sides of the equation. Now, why would we do this? Well, if we look at the expression on the left-hand side of the equation, we're taking n and we're subtracting 5 from it. So to undo this, we're going to add 5. And negative 5 plus positive 5 is 0, and now we have n by itself. And we end up algebraically, we've gotten to the same place, n equals 15, that equivalent equation. So this is an example of the addition property of equality, which says that the same real number or algebraic expression may be added to both sides of an equation without changing the solution. So the formal statement says if we start off with two expressions that are equal, then adding the same number or algebraic expression to both sides leaves the solution unchanged. So our goal when solving a linear equation in X is to find an equivalent equation in the form X equals a constant. So let's look at some examples of what that is. For example, we want to end up with something like X equals 2. Why do we want this? Well, the solution to the equation X equals 2 is obvious. It's 2. We might end up with T equals 5 if we have a linear equation in T. What we end up with might look like 5 equals T rather than T equals 5. And these two equations clearly have the same solution. They're equivalent. So we'll see that we'll be able to switch the left-hand and right-hand side of an equation without changing the solution. And that actually has a fancy name. It's called the symmetric property of equality. And this is the property that allows us to switch the left and right-hand sides of an equation. So T equals 5 is the same thing as 5 equals T. And in general, A equals B is the same thing as B equals A. So let's use the addition property of equality to solve some linear equations. So my equation here is T minus 20 equals negative 50. I want to get T by itself. I want to end up with an equivalent equation in the form T equals a constant. So what I'm going to do here is add 20 to both sides. And why did I do that? Because negative 20 plus 20 is 0, and T plus 0 is just T. So I end up with the equivalent equation, T equals negative 30, and I know the solution to that equation, it's negative 30. So now I want to check this proposed solution. So if T equals negative 30, then T minus 20 is negative 30 minus 20, and when I evaluate that, I end up with negative 50, which is exactly what I wanted. That was the value on the right-hand side of the equation. So now I need to state what my solution is. So the solution to the equation T minus 20 equals negative 50 is negative 30. Let's try it again. X plus 7 equals 3. Now in this example, I have my unknown x and I'm adding 7 to get 3. So to undo that, I would like to subtract 7. And we know that subtracting 7 is the same thing as adding the opposite. Now typically I wouldn't write this second line. I would just write x plus 7 minus 7 equals 3 minus 7. But I just wanted to point out that I'm indeed using the addition property of equality when I subtract the same number from both sides of the equation. So on the left-hand side I have x, and on the right-hand side I end up with negative 4. So I've come up with an equivalent equation in the form that I want, and the solution to this equation, x equals negative 4, is obvious. The solution is negative 4. So let me check this proposed solution. If x equals negative 4, then x plus 7 equals negative 4 plus 7, which equals 3, which is precisely what I wanted. So my conclusion is the solution to the equation x plus 7 equals 3 is negative 4. Here's another example. This looks more complicated because of all the fractions, but we're going to see that the addition property of equality will work just as well here. Now in this equation, my variable p is on the right-hand side. There's nothing wrong with that. But I'm just going to switch the two sides of the equation. You don't have to do this. I just happen to like my variables on the left-hand side. So now I want to isolate p. I want p equals a constant. So since I've been subtracting 1/4 from p, to undo that, I need to add 1/4. And if I add 1/4 to the left-hand side, I have to add it to the right-hand side as well. So now I have p on the left, and here I see I'm going to have to add fractions. So I'm going to start thinking about my common denominator. What's a common multiple of 6 and 4? Well, there are lots of them. 12 is the smallest, and that's the one I'm going to work with. So I'll multiply 5/6 by 2/2 and 1/4 by 3/3. So I have 10/12 plus 3/12, which is 13/12. So I've ended up with the equivalent equation, p equals 13/12. So this gives me my proposed solution, which is 13/12. So let me check this. If p equals 13/12, then p minus 1/4 equals 13/12 minus 1/4. I can see that I'm going to need a common denominator, so I'm going to multiply 1/4 by 1 in the form of 3/3 at this stage of the game. So I have 13/12 minus 3/12, which simplifies to 10/12, and 10/12 reduces to 5/6. So my conclusion is the solution is 13/12. Now here's an equation that looks a lot more complex than the ones that we were just solving. In this example, we're going to combine like terms before we use the addition property of equality. So I'm going to start by writing down my equation. And on the left-hand side, I see I have 6x and negative 5x, which are like terms. 6x minus 5x is 1x. 4 minus 6 is minus 2. And when I combine like terms on the left, I suddenly have an equation that looks just as simple as the ones we were just solving. So I'm going to continue by adding 2 to both sides to isolate the variable. So I end up with x on the left and 12 on the right. This equivalent equation has the obvious solution 12, so that's my proposed solution, which I'm going to check. So if x equals 12, then, and when I do this problem, I'm going to start, and actually I want to check my solution in the original equation, because I may have made an algebra mistake combining like terms, or perhaps an arithmetic mistake. So I'm going to check my proposed solution in the original equation. So 6x plus 4 minus 5x minus 6. When x equals 12, that's 6 times 12 plus 4 minus 5 times 12 minus 6. 72 plus 4 minus 60 minus 6. Let's see, going from left to right here, 76 minus 60, that's 16, minus 6 is 10, and that's precisely what I wanted. So the solution is 12. Now in this example, there are variable terms on both sides of the equation. We have 3m equals 2m plus 10. But I can still use the addition property of equality to solve this equation. So my goal is going to be the same. I want to get m equals a constant. So the way I'm going to do that is I'm going to move the 2m from the right-hand side of the equation to the left-hand side of the equation. And I'm going to do that by subtracting 2m from both sides of the equation. So 3m minus 2m is 1m, or just m, and on the right, I'm just left with 10. So in just one step, I really ended up with an equivalent equation in the form that I wanted, m equals 10. The solution to that equation is obvious. It is 10. So let's check that proposed solution. So if m equals 10, now in this check, I have to evaluate the expression on the left-hand side for m equals 10, and I'm also going to have to evaluate the expression on the right-hand side for m equals 10, and I'm going to hope that I end up with the same thing in both cases, because those two sides must be equal. So 3m equals 3 times 10, which equals 30. And 2m plus 10 equals 2 times 10 plus 10, which is 20 plus 10, which equals 30. So the left-hand side and the right-hand side evaluate to the same number when m equals 10. So we have our solution. The solution is 10. So now we're going to talk about a multiplication property of equality, which we can also use to solve some simple linear equations. Here's one that's real simple. 5t equals 10. We're looking for some number. We multiply it by 5, we get 10. 2 will probably work. 5 times 2 equals 10. So we're aiming for this equivalent equation, t equals 2, because 5t equals 10 and t equals 2 have the same solution, 2. So those two equations have the same solution, they're equivalent. The solution to both equations is 2. So our goal again is going to be to go from 5t equals 10 to t equals 2 using some algebraic properties so we can solve more types of equations. So here's one strategy. Let's start with 5t equals 10 and let's divide both sides of the equation by 5. So 5t divided by 5 should equal 10 divided by 5. 5 divided by 5 is 1. And we end up with that equivalent equation, t equals 2. Now there's another way to look at this. We could start with 5t equals 10, and rather than dividing by 5, we might multiply by 1/5. We know that dividing by 5 is the same thing as multiplying by the reciprocal of 5, so we're just looking at that relationship between division and multiplication again. Why do we do this? 1/5 times 5 is 1. 1 times t is t. 1/5 of 10 is 2. So in this strategy, we also end up with the equivalent equation that has the solution 2, which is the same solution as 5t equals 10. Now what we've just seen here is the multiplication property of equality. Both sides of an equation may be multiplied by the same non-zero real number without changing the solution. So here it's important that we multiply both sides of the equation by some number other than 0. In the example I just did, we multiplied both sides of the equation by 1/5. Why do we have to throw 0 out? Well, what I'm going to do is I'm going to start with a false statement. Here's the false statement. 2 equals 3. No one would believe that's true. But if I multiply 2 times 0 and I multiply 3 times 0, I end up with 0 equals 0, which is a true statement. We started with something blatantly false, but when we multiplied both sides by 0, we ended up with a statement that was true. We don't want this to happen when we're solving linear equations. So we have this condition that we can only use the multiplication property of equality as long as that constant that we're multiplying both sides of the equation by is not 0. So let's solve some equations using this property. So we have the equation 2/3 x equals 12. Our goal is still the same. We want an equivalent equation in the form x equals a constant. So I want to isolate x. Right now, the coefficient on x is 2/3. I want a coefficient of 1. So what can I multiply 2/3 by to get 1? The reciprocal of 2/3. So I'm going to multiply both sides of the equation by 3/2. So 3/2 times 2/3 is 1. So I have 1x on the left. And 3/2 of 12, I'm just going to do some arithmetic in my head here. Let's see, 2 goes into 12 6 times. 6 times 3 is 18. Another way you could do that is 3 times 12 is 36. 36 divided by 2 is 18. We come up with the equivalent equation, x equals 18. Just like before, we definitely want to check our proposed solution and then say what the solution is. So if x equals 18, then 2/3 x is 2/3 times 18. And let's see, if I write this as 18 over 1, I have 36 over 3, which is 12. That's what I want. So the solution is 18. Here's another equation. It's actually very similar to the one we just did. T over 4 equals 25. Now, one of the things we could do, although we don't have to write out this step, is that we could rewrite the expression t over 4 as 1/4 t equals 25. Now, it's clear that the coefficient of t is 1/4. I can multiply both sides of the equation by 4. And I end up with t equals 100. Now, I didn't have to write this line. I could have multiplied both sides of the equation in the original form by 4 and had ended up with the same equivalent equation. So now I want to check my proposed solution and say what the solution is. So if t equals 100, then t over 4 equals 100 over 4, which, what do you know? It's 25. So the solution is 100. Another example, 20 equals negative 6x. In this case, I'm going to divide both sides of the equation by the coefficient of x, negative 6. Negative 6 divided by negative 6 is positive 1. 1 times x is x. And over here I have 20 divided by negative 6. That reduces to negative 10/3. Now, I could leave my equivalent equation this way, but I just like to have my variable on the left. So I'm going to rewrite this equivalent equation as x equals negative 10/3. And I know what the solution to that equation is. It is negative 10/3. So now I have to check this proposed solution in my original equation. So if x equals negative 10/3, then my variable term is on the right-hand side. So I'm going to evaluate negative 6x for x equals negative 10/3. And let's see, I have negative 6 times negative 10, that's 60 over 3. That's 20. That's precisely what I wanted. So the solution is negative 10/3. Now we're going to do a couple more examples, and these are fairly simple examples, but I want to point out some patterns that emerge when we use the multiplication property of equality. My equation is the opposite of z equals 10. Well, I want z equals a constant, not the opposite of z equals a constant. So I've got this minus sign here that I have to deal with. Well, what I'm going to do is I'm going to multiply both sides of this equation by -1. Multiplying a number or algebraic expression by -1 changes the sign. So I have z on the left, and I end up with the opposite of 10 on the right. So here's two equivalent equations. Z equals -10. The solution to that is -10. Now, before I check my proposed solution, which I'm pretty sure is right, notice what happened. When I multiply both sides of the equation by -1, the negative sign on the left shows up on the right. That was the basic effect of multiplying both sides by -1. I didn't check my solution. Let me do that. If z equals -10, then the opposite of z equals the opposite of -10, which is indeed 10. So the solution is -10. Let's look at another example. The opposite of z equals -4. I'm going to do the same trick. I'm going to multiply both sides of the equation by -1. And I have z equals 4. Now notice what happened. When I multiplied both sides by -1, I had a negative on both sides of the equation. Now I don't. So checking, if z equals 4, my proposed solution is 4, then the opposite of z equals the opposite of 4, and that was pretty obvious. So the solution is 4. Now, I'm just going to take this last example we did and solve the same equation using the addition property of equality, just to show you that there might be more than one way to get to the solution. So I have the opposite of z equals -4. I'm going to just use the addition property of equality. I want to get z equals a constant. So one thing I could do is I could add z to both sides of the equation. So now I have the opposite of z plus z, that's 0, and -4 plus z on the right. Now to get z by itself on the right-hand side, I can add 4 to both sides of the equation. -4 plus 4 is 0, 0 plus z is z, and I have z equals 4, which, using the symmetric property of equality, is equivalent to the equation z equals 4, which is exactly what I ended up with when I used the multiplication property of equality. So that was certainly the long way to do that problem, but it's just a demonstration that sometimes there's more than one way to get to a correct solution. So in all of these examples, I've been taking the time to check the solution I proposed for each one of these linear equations. So I want to say a few things about checking solutions. So here's a very simple equation. It looks just like the equations we've been solving. We're told to solve the equation, and we're reminded to check the solution. So I'm just going to show you a solution here. So here's the solution. The student went through, did all these steps, and came up with the equivalent equation, x equals -30. Here's a check. If x equals -30, then the opposite of x plus 5 equals, and you know, they did all these calculations and ended up with 35 rather than 25. And this is going to happen to you, it happens to me, and we have to figure out what to do in this situation. So there are a couple of things that might have gone wrong when a solution does not check. First thing that might be wrong is that an arithmetic mistake may have been made during the check. This is the thing that frequently happens to me when I'm checking a solution. The other thing that might be wrong is that there might have been an algebra or an arithmetic mistake made while solving the equation. So we have two things to check. First, we have to check the check, And then we need to go back and check our solution if the check was okay. So let's do that with this particular equation. So I'm going to check the check first. The proposed solution came from the equivalent equation x equals negative 30. So if x equals negative 30, then the opposite of x plus 5 is the opposite of negative 30 plus 5. Let's see, opposite of negative 30 is positive 30. 30 plus 5 is 35. Arithmetic seems to be okay in the check. So now let's check the solution. The opposite of x plus 5 equals 25. I might just make sure I solved the right equation. I did. Okay, so that's the right equation. Okay, so what am I going to do? I'm going to subtract 5 from, oh, there's a mistake. 5 was subtracted from one side of the equation, but added to the other side. So let's look at a correct solution. Same first line, subtract 5 from the left-hand side, subtract 5 from the right, and we come up with the opposite of x equals 20 now. Multiply both sides of the equation by negative 1, we get x equals negative 20. And when we check this equation, if x equals negative 20, then the opposite of x plus 5 is the opposite of negative 20 plus 5, which is 20 plus 5, which equals 25, and everything checks. Now, one of the things I want to point out is you might say, well, you should have been able to see that we subtracted 5 from one side and added 5 to the other. But as we get better at solving linear equations, a lot of the arithmetic might be done in our head. And that's when these types of mistakes are often made. So let me just summarize some of the things we looked at. Equivalent equations have the same solution. We're interested in equivalent equations because our goal is to find an equivalent equation in the form x equals a constant, or perhaps t equals a constant, or z equals a constant, whatever the variable happens to be. The symmetric property of equality is what I use when I switch the right and left-hand sides of an equation, and we can always use that. And the last thing that we were just talking about, solutions must be checked, and we have to state a conclusion. We need to say what the solution is. So with that, I'm going to turn things over to Candace, who's going to solve linear equations where we use both the addition property of equality and the multiplication property of equality in one problem to solve a linear equation.
I'm going to talk some more about equations of the form Ax plus b equals c, and I'm going to combine the addition property of equality and the multiplication property of equality. First, I'm going to look at a couple of introductory examples, and then I'm going to look at a strategy for finding the solution and go through some examples using the strategy. So let's start with our introductory examples. Suppose I want to find the solution to 2x plus 5 equals 17. My goal is to isolate x. I want an equation of the form x equals a constant. The first thing that I'm going to do is work with these constants 5 and 17. Since 2x is already on the left-hand side of the equation, I'm going to move my constants to the right-hand side of the equation. So since I'm adding 5 on the left-hand side, if I subtract 5 from both sides of the equation, I can move all of my constants to the right-hand side. So 2x plus 5 minus 5 will equal 17 minus 5. That leaves me with 2x on the left-hand side of the equation and 12 on the right-hand side of the equation. So I used the addition property of equality to add negative 5, which is the same as subtracting 5 from both sides of the equation. Now I'm going to use the multiplication property of equality to isolate x. I need to get rid of that 2 that's being multiplied by x. I can do that by multiplying both sides of the equation by the reciprocal of 2, which is 1/2. So 1/2 times 2x equals 1/2 times 12. Notice that I could have also divided both sides of the equation by 2. That's the same as multiplying by 1/2. I just chose to multiply by 1/2. 1/2 times 2 is our multiplicative identity, 1, and 1 times x is x. So I just have x on the left-hand side, and on the right-hand side, 1/2 of 12 is 6. So I have an equivalent equation to the original equation, and this equivalent equation is x equals 6. Let's go ahead and check the solution. If x equals 6, then looking at the left-hand side of the equation, since that's the side where the expression involves a variable, 2x plus 5 equals 2 times 6 plus 5, and that's 12 plus 5, which is 17. This checks. The right-hand side of the equation is 17. The left-hand side of the equation evaluates to 17 when x equals 6. So now I can state my conclusion. So I can say the solution to the equation (2x plus 5 equals 17) is 6. Let's try another one. What if I wanted to find the solution to 9 equals 5x minus 11? This time the only term that involves a variable is 5x. I want to isolate the variable x, so I'm going to go ahead and move my constants to the left-hand side of the equation. I can do that by adding 9 to both sides of the equation. No, I can do that by adding 11 to both sides of the equation. I want to get rid of the minus 11 by the 5x here. So if I add 11 to both sides of the equation, 9 plus 11 equals 5x minus 11 plus 11. 9 plus 11 is 20. And on the right-hand side, I'm just left with 5x. Now I can isolate the x by either multiplying both sides of this equation by 1/5 or dividing both sides of the equation by 5. I'm going to choose to divide both sides of the equation by 5. 20 divided by 5 is 4. 5x divided by 5 is 1x. 1 times x is x. So I end up with 4 equals x. This is equivalent to x equals 4. So let's check the solution. If x equals 4, then looking at the right-hand side, since that's the side that involves the variable, 5x minus 11 equals 5 times 4 minus 11. 5 times 4 is 20. 20 minus 11 is 9. And this checks. The left-hand side of the equation is 9. The right-hand side of the equation evaluates to 9 when x equals 4. So now I can state my conclusion. The solution is 4. Now I want to look at a strategy for finding the solution. When we're solving equations of the form Ax plus b equals c, generally the first step is to use the addition property of equality to isolate the variable term or terms on one side of the equation and the constant term or terms on the other side of the equation. Then, after simplifying each side of the equation, we'll use the multiplication property of equality so that the coefficient on the variable is 1. Next, we need to check our proposed solution to the original equation and state our solution using a complete English sentence. So let's use this strategy to find a solution to negative 44 equals 100 minus 12t. So I start by noticing that I have a variable term, negative 12t, on the right-hand side. I'm going to move my constants to the left-hand side of the equation. I can do that by subtracting 100 from both sides of the equation. So negative 44 minus 100 equals 100 minus 12t minus 100. Negative 44 minus 100 is negative 144. And on the right-hand side, I'm just left with negative 12t. Now to isolate t, I'm going to divide both sides of the equation by the coefficient of t, negative 12. Negative 144 divided by negative 12 is 12. Negative 12t divided by negative 12 is just 1t, which is t. So I end up with the equivalent equation 12 equals t. This is the same as t equals 12. Let's check the solution. If t equals 12, then 100 minus 12t equals 100 minus 12 times 12, which is 100 minus 144, which is negative 44. Exactly what I wanted. The left-hand side of the equation is negative 44. The right-hand side of the equation evaluates to negative 44 when t equals 12. So I can state my conclusion. The solution is 12. Now let's find a solution to 5x minus 3 equals 7x plus 9. The first thing I notice about this equation is that there are variable terms on both sides of the equation and constants on both sides of the equation. So I'm just going to make a choice here. I'm going to move my variable terms to the left-hand side of the equation and my constants to the right-hand side. To move my variable terms to the left-hand side of the equation, I would need to subtract 7x from both sides of the equation. So let's do that. 5x minus 3 minus 7x would equal 7x plus 9 minus 7x. 5x minus 7x is negative 2x. So on the left-hand side, I have negative 2x minus 3 equals, on the right-hand side, I'm just left with 9. Now that my variable term is on the left-hand side, I want to move my constants to the right-hand side. I can do that by adding 3 to both sides of the equation. So negative 2x minus 3 plus 3 equals 9 plus 3. So I'm left with negative 2x on the left-hand side and 12 on the right-hand side. Now to isolate x, I'll divide both sides of the equation by negative 2. Negative 2x divided by negative 2 is just 1x, which we write as x. 12 divided by negative 2 is negative 6. So I get the equivalent equation, x equals negative 6. Let's check that solution. If x equals negative 6, then I'm going to need to evaluate both sides, both expressions on the left-hand side and the right-hand side when x equals 6. Let's just start with the left-hand side, 5x minus 3. So that would be 5 times negative 6 minus 3, which is negative 30 minus 3, which is negative 33. And if x equals negative 6, then the right-hand side, 7x plus 9, would evaluate to 7 times negative 6 plus 9. That's negative 42 plus 9, which is negative 33. So my solution checks. Both the left-hand side and right-hand side of the equation evaluate to negative 3 when x equals 6. So I can go ahead and state my conclusion. The solution is negative 6. Now let's look at this problem one more time. 5x minus 3 equals 7x plus 9. The first time I found the solution to this, I made a choice to move my variable terms to the left-hand side of the equation. That was just a choice. It doesn't matter which side the variable terms are on and which side the constant terms are on. So what would have happened if I had moved my variable terms to the right-hand side of the equation? To do that, I would need to subtract 5x from both sides of the equation. So 5x minus 3 minus 5x equals 7x plus 9 minus 5x. So I'm left with negative 3 on the left-hand side of the equal sign. 7x minus 5x is 2x, so I have 2x plus 9 on the right-hand side of the equal sign. Now I want to move my constants to the left-hand side of the equation. I can do that by subtracting 9 from both sides of the equation. So negative 3 minus 9 equals 2x plus 9 minus 9. Forgot what I was subtracting there. Negative 3 minus 9 is negative 12. And 2x plus 9 minus 9 is just 2x. Now to isolate x, I need to divide both sides of the equation by 2, the coefficient of x. So negative 12 divided by 2 equals 2x divided by 2. Negative 12 divided by 2 is negative 6. 2x divided by 2 is x. So we get the equation negative 6 equals x, which is the same as saying x equals negative 6. Either way, the solution is negative 6. Now let's find the solution to 9y minus 1 equals 11y plus 2. Since it doesn't matter what side I move my variable terms to, I get to make a choice here. Do I want to move my variables to the left and my constants to the right, or vice versa? I think I'll move my variable terms to the left-hand side of the equation. To do that, I would need to subtract 11y from both sides of the equation. So 9y minus 1 minus 11y equals 11y plus 2 minus 11y. 9y minus 11y is negative 2y. So I have negative 2y minus 1 on the left-hand side of the equals. On the right-hand side, all that I have left is 2. Now I'm going to move my constants to the right-hand side of the equal sign. So I need to add 1 to both sides of this equation. Negative 2y minus 1 plus 1 equals 2 plus 1. So I'm left with negative 2y on the left-hand side of the equation and 3 on the right-hand side of the equation. To isolate y, I need to get rid of that coefficient, negative 2. I can do that by dividing both sides of the equation by negative 2. So negative 2y divided by negative 2 equals 3 divided by negative 2. This simplifies to y equals negative 3 halves. Let's check the solution. If y equals negative 3 halves, then we need to evaluate each side of this equation when y equals negative 3 halves. So 9y minus 1, the left-hand side, equals 9 times negative 3 halves minus 1. I'm going to go ahead and write 9 as 9 over 1, since I'm going to be multiplying fractions. Multiplying the numerators, 9 times negative 3 is negative 27. Multiplying the denominators, 1 times 2 is 2. And 1 I can write as 2 over 2, which will give me a common denominator. Negative 27 halves minus 2 halves is negative 29 halves. Now I want to evaluate 11y plus 2 when y equals negative 3 halves. So if y equals negative 3 halves, then 11y plus 2 equals 11 times negative 3 halves plus 2. I'll write the 11 over 1. 11 times negative 3 is negative 33. For my numerator, my denominator is just 1 times 2, which is 2. Plus 2 I can write as 4 halves. 4 divided by 2 is 2, and I have the common denominator. Negative 33 plus 4 is negative 29. So negative 33 halves plus 4 halves is negative 29 halves. And my check works. Both the left-hand side of the equation and the right-hand side of the equation evaluate to negative 29 halves when y equals negative 3 halves. So let's go ahead and state the conclusion. The solution is negative 3 halves. That concludes this lesson on solving equations.